All right, so today we're going to be taking a look at weather, climate, and atmospheric movement, including convection currents in the atmosphere. So weather is the current state of the atmosphere. In other words, what's happening right now. Is it sunny outside? Is it 72 degrees? Is it raining? And so this is what is happening right now. So this is what you would see when you see weather. A 5-day forecast. On Sunday, it's going to be 75 degrees. Monday, 72 degrees, but a bit cloudy. Tuesday, 4,298 degrees as the comet hits the Earth. Wednesday and Thursday, no temperature because the Earth doesn't exist anymore. Climate, on the other hand, is long-term atmospheric conditions in a region. So this is not just your daily changes. Weather changes daily, but climate is long-term averages. And so I'm going to give you a couple examples for you guys to look at in just a second. And these examples are going to be looking at average temperature and precipitation in Houston. So up in the top left-hand corner, you see the average temperature range in Houston. And we have red meaning highs, blue meaning low temperatures. And we see that for the entire year. And we can see a very distinct curve here. On the top left-hand corner, you see the average monthly precipitation in Houston. And so in May and June, it tends to rain a lot more than it does in February or July or August. And so you can see how this monthly precipitation averages out over time. Now at the bottom, you'll often see graphs when it comes to climate represented twofold, where you have the average temperature as well as the average monthly precipitation. This helps to give you an idea of how temperature can affect precipitation as well. So once again, climate is long-term atmospheric conditions in a region. So some main points to remember as we learn about weather is that air above land is warm more quickly than above water. So it takes essentially longer for water to warm up than the air than air does above land. And so that's also going to be important in the fact that water also cools down slower than air above land. And so this is going to help create a couple things. Also, warm air expands and rises, creating an area of low pressure. So something you might want to add into your notes. So warm air equals low pressure, and cool air equals high pressure. Cold air is dense and sinks, creating an area of high pressure. So let's take a look at these two pictures and discuss what's occurring. So as we said, air above land cools and heats faster than air above water. And so during the day, this air above the land is going to heat quicker, causing it to rise up. Now, as it rises, it begins to cool back down and fall. Now, since this air is rising, the cooler air rushes in to fill the void. And so this is a convection current. As the low pressure warm air rises, the high pressure or denser cold air moves in to take its place. And this is going to result in a sea breeze. Now, at night, that air over the water is going to take longer to cool down than the air on land. And so now we have high pressure on land, low pressure in the water, over the water. And so we have an opposite effect, where the high pressure air, the low pressure air over the water is going to rise, and the high pressure air on land is going to move in to fill the gap, creating another convection current in a process we call land breeze. So to put this in perspective, imagine you spent 24 hours standing on a beach in Galveston. So during the daytime, the wind would be blowing, and say you're facing the ocean. You're going to be facing the ocean. All right? And so during the daytime, the wind would be blowing in your face, because that high pressure air, or the high pressure cooler air, is going to be rushing in to fill the void of the low pressure air, the warmer air that's rising. But at night, we have the opposite occurring, with the land air getting colder quicker. And so that high pressure air is going to be blowing at your back, so the wind be coming from behind. So during a sea breeze, it's coming from the sea, and night, a land breeze is coming from the land. So I want to explain high pressure versus low pressure air really quick. So what I'm going to do is I'm going to draw a couple of boxes here. Let me move my computer. Okay, so I'm going to label this as my high pressure. You know what? Actually, I'm going to change the colors here. So this is my low pressure, and this is going to be my high pressure. Okay, and I'm using these colors specifically because high pressure is cool air and low pressure is warm air. Okay, so just like what we talked about with phase changes, You can imagine the high pressure as being a lot more dense. Okay, so I'm just going to use some lines to show that it's full. So all the molecules are more closely packed together because they're cooler, because heat is energy. But the low pressure is much more dispersed. And in a convection current, you have your low pressure air rising. Okay, your low pressure air will be rising, and your high pressure air will be falling. And it's all about moving from high to low concentrations. As the low pressure air rises, it creates a void, and the high pressure air flows in to fill that void. So this creates not just convection currents on land, but it's happening all the time all over the globe, creating giant convection cells in the atmosphere. And so up the top, we have the polar cells, the Ferrel cells, followed by the Hadley cells. And this is going to repeat at the bottom. You have Hadley, Ferrel, polar. And so these convection currents are driven by the energy that is given off by the sun. And so you can imagine that at the equator, since there's a lot more energy, heat energy, directly at the equator, this is where air is going to warm a lot faster. So you can see how we end up with low pressure air being formed right there and rising up. And as it gets further away from the equator, we see it fall. And the same thing is going to happen over here, so on and so forth. And so this creates our global convection currents. And this is going to make different winds. The polar easterlies, the westerly winds, the northeast trade winds, the southeast trade winds, the westerly winds, and the polar easterlies. And you can kind of get an idea of what direction the wind is going to be flowing up there. So, north, east, south, west. So the easterlies are going to be coming from the east. The westerlies are going to be coming from the west, so on and so forth. So these large-scale convection currents are what create our global wind currents. And like I said, you have the easterlies coming from the east, the westerlies coming from the west. In the middle here, we have the doldrums and the trade winds, and we're going to talk about those in just a moment. So intense heat is going to equal powerful convection. So at the equator, where the energy is much higher, you're going to have a lot more convection going on. So warm, moist air rises and leaves behind an area of low pressure. This is why most rainforests are found along equatorial regions. The air rises until it reaches the top of the troposphere, where it can't rise any further. It spreads out towards the polar regions, hot following cold, wanting to share the warmth, kind of like what you talked about in sixth grade of how heat energy transfers. And as it spreads, it begins to cool and sink, usually around 30 degrees north and south of the equator, so just above the Tropic of Cancer and Tropic of Capricorn. Now, this sinking air produces an area of high pressure with dry conditions. And what we'll see is that these 30 degrees north and south of the equator are where a majority of the Earth's deserts are located. So, like I said, some of the air moves back towards the equator as it sinks. And this is going to create a very important thing for history, and that's the trade winds. And so you can see the dominant winds and the trade routes. So you can see how all these trade routes between America, Europe, Africa, South America follow these dominant winds, helping sailors to make the most efficient crossings between the New World and the Old World. So trade winds are winds used by sailing vessels to conduct trade between different continents. So that'll do it for today's tutorial. Remember to like, share, and subscribe to get new tutorials. And this has been Mr. Holsey of 8 Squared, Officially Understood Science. See you next time.